My bad. All right, there we go. Okay, so work external is then just equal to P1 minus P2 dV, right? So then, oh yeah, and then this is also a small part of work done. PV work. Yeah. Yeah, that's kind of, yeah, this makes sense from, this kind of connects to chemistry as well. I'm glad you caught that. So the work is equal to the difference in pressure dV, right? And then, we can make this a differential. So then dW dV is just equal to the difference in pressures, right? Yeah, I believe, yeah, you're a sophomore, right, Lewis? Yeah, you're taking chemistry. Okay, so we have dW dV is equal to the difference in pressures. What now? Well, what else is dW? dW is equal to the change in energy, right, as we saw here. So this is half mv squared minus half mv squared plus uh, mgh minus mgh, right? Okay, so now we want to get these two in a similar form. So what I'm going to do is I'm going to divide by dV, all right? This sounds very cursed from a calc perspective, but it is what it is. So dW dV is equal to half. Now, if I put the dm with the dV, right? So what does this become? dm dV. Yeah, this is the density, mass over volume, right? So I can actually just write this as rho because we're assuming our liquid to be uniform. And then, we can do the same thing here because we have all dm's, right? And then dm dv just all becomes uniformly rho. So half rho v1 squared plus rho gh2 minus rho gh1. And this is equal to the difference in pressures. Right? So then if we move all the ones and all the twos to their respective sides, then we just get a half rho v2 squared plus rho gh2 plus, when you post in fluids class notes, after this lecture, probably, plus P2 is then equal to half rho V1 squared plus rho GH1 plus P1. But then we notice that like these two, they have the exact same structure, right? Which means that we can actually take like any increments of distance along your pipe, and then like this will remain the same, right? So then therefore, this just becomes a conservation law. So we have like conservation. Uh, so at any point in a body of fluid, this combination remains constant, right? So half rho v, well, there's no subscript anymore because it's just in general. So the speed of the water particle cannot be differentiated with time to set it equal to 0. I don't exactly know. Well, you can like, you can look into that if you want to, but I don't think there's a use for differentiating it with respect to time though, because this is a conservation law, right? I don't know. I don't really see a point in differentiating. Yeah. Anyways, so this quantity remains constant. Okay, and this is the thing I wanted to finish up from last time. Okay, any questions? Any questions? So if not, we're going to move on to a problem. Well, it's not exactly conservation of energy because there's also fluids in there. I mean, there's also pressure in there, right? So then it's more just like a general fluid conservation law. And then, well, yeah, it's kind of like energy conservation in fluid. But then like energy conservation also just holds in general, right? So this is kind of just its own thing. Okay. Um, I will give you a problem. Okay. So let's just say you have a container full of water. Right. And then the container of water has a height of h, right? And then it's filled with water. Okay, so when you puncture a hole, when you puncture a hole in your tank, what's going to happen to the water? It's going to flow out, but floosh. Okay, but what's going to happen to it? Like if I focus on one water particle, right, and it's the exiting the container, isn't it? Okay, let's ignore cohesion. Actually, it's not going to stick to the edge. Yeah, so let's just say this is H, right? It's going to collapse because of the lack of water holding it up. Uh, no, I'm not saying, yeah, the water level will eventually go to H. Yeah, but then, no, I'm not, no, not evaporate. No, I'm saying like at the instant that it's punctured. So what trajectory is this water particle going to follow? Yeah, it's going to be parabolic, right? Because it's just going to like flow out through your hole. And then after that, the only thing that is governing its motion is just projectile motion, right? And it's going to flow out and, have some trajectory. Okay. And then let's call this distance r. Okay, so now here's my question. So at what h is the initial r the greatest? And what is that r? All right, so take a couple of minutes to do this problem and DM me answers. All right. So an obvious hint would, of course, to be to use the thing that I just talked about, which is Bernoulli's equation. Oh yeah, and then assume that the tank of water is perfectly still before you make the puncture. Yeah. I don't know. You can just pick one and see what happens. But there's probably one that's like easier, I'd say. Ooh, also another important clarification, the top is open. Sorry. Ooh. No, it's okay. It makes the problem simpler, if I recall correctly. All right, I have one answer. Um, I feel like you calculated your R wrong, but the H looks good. Come on, man, the R is supposed to be the easier part. All right, how much more time do y'all want? Like 5 more minutes? Is that okay? A lot of time. Please don't say like an hour. I have I have more things to talk about. All right, I'll give you guys until 5:15. 17 hours. Okay, tell you what, do you want to leave this for like no. Actually, yeah, do you want to leave this for next week? So you have like one more week to work on it along along with the extra FMA test. Do you want an extra week? You're just gonna forget about it. All right, 5:15 then. All right. Lewis, you look like you were the closest to a solution. Uh, do you have like another value of R that you got from recalculating? All right. You know what? It's fine. Do you want to present the first part? Because
Uh,
that's like the more important part, I think.
well,
Can
I
you?
kind of got it. I got it from the value of R I had, so I don't know how I could have messed up one and gotten the other right.
Huh?
I got
Um, wait,
I
how do
know.
you get R first? I'm confused.
No, I got no, like they're intertwined from how I used the Bernoulli equation. So I can't
Oh, I see.
I don't I think that I don't see if how my answer could be right in one but not the other. So I'm probably just wrong in both.
No, no, you're right in the first one.
No, I know, but I think my strategy was wrong. I don't know. I think I just got the same answer by luck.
Wait, let me actually check. So what does that turn into? You have like root 2 big H minus small h times h. So what is this? Um, yeah, that doesn't look too right. Yeah, I don't know, man. Okay, wait, there's a question. Do you sub in pressure for Bernoulli's equation? Like P equals to rho GH plus PA. Ooh, what's your PA? Atmosphere? No, not exactly. All right, so I'm gonna give you guys the key observation that is made that should be made here. All right. So the key observation is that um there's a pressure here, right? The pressure at H is actually also just equal to ATM. And this is because there's a hole, right? So if you have a gas or fluid of one pressure in one container, and then a fluid of another pressure in the other container, when you puncture a hole in between the two, then the pressures at like inside of these two containers, they tend to equalize actually. And then which is and this is the key observation that allows you to carry on with the rest of the problem. So just by a show of hands, like who actually got there? Yeah, the container for the atmosphere is the universe itself. Yeah, so everything that's outside of the container just has pressure of ATM. And as soon as you cut a hole in between them, the pressure like at the point where the hole uh, is becomes the same as the atmospheric pressure. So does anyone have any questions? Wait, why is that? Well, the reason kind of lies in how, you know, things move from lower concentration to higher concentration. And then, you know, because of the hole, you know, the water wants to move from like a place with higher pressure to a place of lower pressure, right? But then at the same time, like air kind of goes in, I think. And then yeah, I think the reason is actually more rooted inside of chemistry, so I'm not so sure. But yeah, I think there was some reason stated in chem that I forgot. I don't know. Did anyone in chem like learn this and want to explain? why pressure equalizes when you open a hole between two containers. Orlando's a chem teacher that I think a lot of us had. Does anyone have an explanation from their chem class? Because I forgot the reason, but this is a thing that happens. So, yes, the same reason why temperatures tend to balance out. Yeah, this is kind of the intuition that I had, but diffusion something. Yeah, pressure gradient. Okay. But this is the key observation that we want to have, right? And this is because hole exists, so pressure equalizes. Okay. So from here, we can just write out the Bernoulli equation. Now, what I'm going to do is I'm going to compare like the Bernoulli equation at the top of the container and where the hole is, right? So we have half rho v top squared plus rho g h. Well, this h is going to be big H, right? Because we're taking the top of the container, plus the pressure here, which is ATM. The pressure at the top is going to be ATM. This is going to be equal to half rho v at the whole squared plus rho g small h plus ATM again, right? Because of our observation. So then from here, these two just cancel out. But also because we said that at the beginning, the water is completely still, right? We can also say that V top is equal to 0. All right, Lewis, you're almost there. It's supposed to be R equals to H. I'm pretty sure. It's okay. So V top is equal to 0. Because like there's nothing really to disturb it and there's no real forces acting on it. So this means we can just completely disregard half rho v top squared, right? So then what we're left with is rho g h is equal to half rho v whole squared plus rho g small h. We can kill off the rho's, right? And then we get g times big H minus small h is equal to half v whole squared. Okay, so v whole squared is equal to, or I'm just gonna put the normal v, all right? So v whole is equal to the square root of 2g times h minus h. All right, so with that in mind, where I have is like, yeah, 2g h minus h. So who can tell me what the time it takes, what the time it takes is for a projectile to go from the top of its motion to the end of its motion, right? Because we want to look at what the projectile does when it's at the top and as it goes down, right? So then this range is equal to VH times T, right? So what is this T? T is the square root of 2H over G. Good. Everyone remember that. Everyone remembers that, right? 2H over G. Well, I can rederive it for you, right? So the time it takes is the same as free fall. So then so then we have like H is equal to negative half GT squared. And then T is, well, we can get rid of the negative sign. So T is equal to 2h over g. Yeah, this is what we get. Anyways, yeah, so d equals to vt plus half at squared, and then v naught, vy naught is equal to 0. So then we have this. Cool. So then from this, we have r is equal to, oops, it's just vh over here. So this is equal to 2g h minus h times 2h over g, right? The g's die, we can bring the 2 to the outside of the square root. So this just becomes 2 times the square root of h minus h over times h. Okay, yeah, so now we have like this expression of r in terms of big H and small h. And then I can call this A and I can call this B, right? So if we know that A plus B is equal to H, then like what is the maximum value of A times B? Yeah, it's when A equals B. AB is max when A equals B equals to H over 2. Yeah, so does anyone, yeah, AMGM as Andrew would say. I guess I can show you this. So A plus B over 2 is greater than, well, this is AMGM, all right. Everyone know what AMGM is? I'm not going to prove it, but I'm just going to use it, right? So the arithmetic mean, which is sum over 2, is greater than or equal to the square root of the product, which is the geometric mean, right? So and this is equal to h over 2, right? So then therefore therefore AB has to be less than or equal to h squared over 4, right? And then this happens when A equals B equals to h over 2. Okay, so now that we have that, we can replace A and B with h minus h and h, right? And then when they're both big H over 2, then this becomes h over 2 times h over 2, which is just 2 times h over 2, which is just equal to h. All right, and this is equal to the maximum range. And the maximum height is equal to big H over 2. Any questions? This was kind of a big problem, but we did all right. Okay, so it's around 5:30. I'll give you a 10-minute break right now. Yeah, I'll see you all at 5:38. Or let's just go to 5:40. Why not? But of course, like if you have any questions, you can stick around and ask. Yes, resume the recording. Um, all right, so just as a quick review, I want to go over just some like basic things about dimensional analysis and units. All right, so the basic and fundamental quantities per units are for mass, length, and time. right? And this is usually measured in like kg, kilograms, meters, and seconds, right? And then everything else can be derived from these units. So for example, you have the joule, which is kilograms, meters squared over seconds squared. We have like newtons, which is kilogram meter per second squared. Like what else is there? Uh, there's like the watt, which I think I covered at some point. It's for power, right? So this is for work. I mean, this is for power, which is work over time. So this would be kilogram meters squared over second cubed. Yeah, so then like we have these, right? But this isn't really the most important part. Well, firstly, it should be pretty important that when you check your work at the end of a problem, like the units are right. Because if the units are not right, then that means you did something wrong in the middle of your process, right? Um, so at the end, the units always have to be right. And like this is also a reason why a symbolic answer is always preferred instead of doing something directly numerically. So, and then also with symbolic answers, you can test for, extreme cases, and you can also just easily change whatever you have instead of going back and doing all the calculations again, right? Okay, so I'm gonna start you off on a pendulum, right? And then I want to show you that when you utilize dimensional analysis, you can actually do a lot of physics problems without even knowing any physics. Ooh, someone copy pasted the Morin limerick. Yes, always check your units. Your units are wrong, cried the teacher. Your church weighs 6 joules. What a feature. And the people inside are 4 hours wide and 8 gauss away from the preacher. That is a good poem. So we're going to try to figure out the period of the pendulum. And we're going to pretend that we don't know what this is already, right? Because if we didn't pretend that, then it would kind of defeat the purpose of this demonstration. And also this could be used in more complicated examples. So now you have some pendulum and then, small angle, of course. Okay, so yeah, what quantities? Yeah, I said we're gonna pretend we do not know it already. Right, so what is the, so what measurements are typically given with a pendulum? So what measurements?
Like, what is a period, like in principle? Like, what are we describing when we say, the period is, I don't know, like 3 pi or something?
The period is 3. Okay, S. What is S? Seconds?
Exactly. Which means
Yeah.
that in our fraction or in our whatever, we have to end up with seconds, because otherwise we're not describing a period.
Right, so the units of T, which we write using the brackets, right? The units of T is just equal to seconds. And this is what we're trying to get. So, oh yeah, so what measurements are we usually given when we're talking about a pendulum? We have angle, but we're assuming small angle, right? So we don't actually, the angle actually isn't that important.
Also, we want like non-unitless measures. So if somebody says pi, pi is unitless. We want just things with dimensions.
Yeah, R, what is R?
I think the length of the, I think he means the length of the,
I mean, like,
the thing. Shoot, I'm forgetting what strings are called.
do you mean the length, Ivan?
Yes, okay.
Okay, so we have, I'm gonna call the length L, right? Okay. So we have L, we have G. Anything else? Square root. That's not a measurement.
Square root's not a measurement.
Nothing else
Um,
is really necessary.
what-
Yeah, mass.
Now we're gonna find out that the mass cancels.
No,
But
we don't
before
know that
then-
the mass
Well,
cancels.
yeah, we're gonna find out, but it's important to lay it out. Like, well, you're looking at it with like a hindsight 2020 kind of thing. Like, you know that mass is not in the formula, therefore we shouldn't look at mass. But when you're deriving measurements, it's important to just like lay out every single possible dimension that you could gain from this in front of you. And every single possible one as well, the length of the rope, the gravitational acceleration, and the mass of this thing. Do you think we should factor in the velocity of the thing moving, or do you think that's kind of pointless?
Well, we can.
I mean, I'm asking everybody. Like, do you think we should also take into account how fast the pendulum is swinging? Might as well.
V question mark?
Mhm.
Oh, we actually don't know V. V isn't a direct measurement we can make.
Yeah, that's why I'm asking. So the thing is, we can't take into account how fast it's moving because, we don't know for sure. And, does the period of a pendulum vary on how fast the pendulum is moving? Anyone? Yes, no? You guys want to, I don't know, thumbs up, thumbs down? Or like, yeah, I guess Alvin's pleb status account doesn't let you use other reactions.
Uh,
Okay. Well,
uh,
in any case, yeah, it doesn't depend on it.
if you have a better Zoom account, I invite you to host meetings.
I don't. I think, well, actually, I'm not even sure. Whatever. In any case, no, it doesn't.
So let's proceed, right? So what are the units of G? Use Discord. Now Zoom has like a really nice recording and whiteboard thing. And I think I want to keep on. Yeah, so meters per second squared, right? Okay. What about L? Meters, cool. And the mass? Kilograms. All right, cool. I do not care about updates. Okay. So now, what remains is just to figure out like what combination of G, L, and M gives a unit of seconds. Gives the units of seconds. So then there's two ways of doing this, right? The first way is to say, okay, well, G is equal to, if I take like G to the alpha, right? Because it's always, the unit combination is always going to be like one thing to some power times another thing to another power, and that's going to be the unit of the thing, right? So G to the alpha is equal to meters to the alpha times seconds to the negative 2 alpha, right? And then, L to the beta is equal to meters to the beta, right? And then the mass to the gamma is equal to like kilograms to the gamma. And then basically when you multiply all these together, right, you get m to the alpha plus beta times seconds to the negative 2 alpha times kilograms to the gamma is equal to, did I do this wrong? No, I did this right. This is equal to just s to the 1, right? And then you can solve this system of equations because you have 3 things and 3 variables, and then this will work out. But then, you can also just kind of play around with the units and then until it becomes correct. And in this simple case, it's probably better to just play around with it. But then, when it gets more complicated, you might have to start using this method. So yeah, and then this just becomes solving a system in like 3 variables, and then that's not too bad. But all right, so Mo is saying square root of L over G. Okay, so let's test that. So what are the units of square root of L over G? This is equal to, so L is meters, right? So it's meters over meters per second squared, and the square root of that. This just becomes the square root of seconds squared, and this is equal to seconds. And it turns out that we actually got the right unit combination, which is good, right? So like notice how in this situation, you solve the problem without actually knowing any of the physics behind, like simple harmonic motion and how a pendulum works and all that. Like you solved this problem and you found that the period was equal to L over G just um, purely using just like dimensional analysis. Yeah. Anyone have any questions? But then again, only using the units does not prevent you from, missing a constant factor.
Exactly, Jeremy.
Yeah,
Perfect.
Jeremy, that's exactly. So then you actually do have to use some physics to figure out that there's a constant, right? But then, just like without any physics at all, you've already solved most of the problem. And then, I find that is pretty cool, right? And then the constant here, I'm not gonna, you guys didn't see that. What happens to the constant that is next to square root of L over G? Anyone remember from SHM? What is the constant that is besides L over G?
2i.
2 pi.
Wow. Yeah, complex number. I like it. Gotta move in a different dimension. Yeah, so this can be derived, but this is something that you can't get from just pure dimensional analysis. So, and like, unfortunately, when it comes to the F equals ma, all of them are typically in the right units, but what can differ is the constants and the unitless measures. So you need some physical analysis for that. So how do we perform a physical analysis to determine this constant? Experimentation. Okay, cool. Now, how exactly should we conduct this experiment? We know that the period is proportional to the square root of L over G. So how do we find a constant from that? test period with different lengths. Exactly, because we know G is a constant. So what we can change is L. So, if the period is X amount of seconds with the pendulum of length L1, then we can divide, we can square it, multiply by G, or sorry, we can yeah, we can square it, multiply by G, divide by L, and you get, the constant, right? Because we divided by what it's proportional to, so what should be left is the constant. Now, yes, for a 10, so Lewis has an interesting idea. For a 10-meter pendulum, the coefficient should be the period. So yeah, if we have one where L is equal to G, then that just becomes 1. And so then the period is just the coefficient. Now, at least as far as I know, I don't think this is how they did it because it's imperfect. Like there needs to be like a more systematic way to get that it's 2 pi, because if you notice that it's about 6.28 something something something, like cool.
I think
But
they might have just solved the differential equation.
yeah, so that's the more technical way to solve it.
Define pi by this constant.
Yes,
Yes.
pi is 1/2 of the period divided by that. Mhm.
Yes. Pi is just half the period divided by L over G. This is how we define pi, people. No, I'm joking. How does dimensional analysis apply to trig functions and powers of E that result from different equations?
Okay, so with differential equations, the idea is the power of E comes from the solution, right? So differential equations, like the reason that we always write them as exponentials in terms of like E to the something is because that's the nicest differential, that's like the nicest differentiable function, because what's the derivative of E to the X itself? So it's the nicest like looking thing. So typically when we're looking at linear differential equations, we write them like that. Sorry, not linear, ordinary differential equations, homogeneous, we write them like that. So dimensional analysis doesn't really help with that. That's more just like solving the differential equation and getting that it has to be a certain power. For trig functions also typically come like, do you guys remember a few weeks back we derived the simple harmonic motion equation from the differential equation? Like thumbs up, Y in the chat, whoever remembers that. If you don't remember it, we uploaded the video to YouTube, I'm pretty sure. Yeah, we derived the formula for simple harmonic motion through the differential equation. We did it at an office hours section. And so, cosine of X came from that because, yes, I kind of don't want to go through that derivation again. If you want to look at it, you can look at it. So, yeah, that's typically where trig functions come from, the solution to a differential equation. Because, just noticing it's periodic isn't very scientific. So you have to like really confirm mathematically, definitively that it is periodic. So yeah.
All right, cool. I'm going to show a more complicated example, which is escape velocity. All right, so does anyone remember escape velocity by chance? Mach 23.
No, we mean the equation. Mach 23. No, well, yes, root 2gm over r. Mhm.
All right, like this might be a bit hard to remember at first, right? But then, when you just use some units, this becomes actually pretty easy to derive. You just have to remember the 2, right? So then let's consider some planet with mass of mp, a radius of r, and Okay, and then what else do you think should be given? Like what other quantity? H is the height of the planet. Huh? What's the height of the
Do you mean height from the surface of the planet? Um, anyway, well, consider this. Do you think that it would be easier for a ping pong ball to escape the atmosphere than for a, I don't know, a semi truck? Okay, so maybe the mass of the object itself should come into should be a factor of this, right?
Okay, so let's put that under other quantities. So mass of
MO.
object. What else? And anything else?
Okay, so Jeremy has been writing in the chat like h is the height, like from the surface.
Yeah, we can
So
put that in like R, right?
you want to leave that in R? Okay. Yeah, h doesn't matter, but you know, it's always important to
Okay, so what other thing are
recognize.
we given? Lewis has nice thing.
Is there any other, like, I don't know, maybe,
I mean, Lewis gave the answer, but we're gonna ignore that for now.
yeah, in terms of like in terms of gravitational forces, you know, it's got to be escaping from something, right? So maybe the gravitational force imparted by the planet has something to do with this. Because I think it's easier to escape from the Earth than it is from from the moon than it is from the Earth, right? No, nobody concurs.
Yeah. So Lewis got it. The other thing that we are given is G, right? Or big G. Okay. Um, so now let's try to figure out what the escape velocity is, right? So we have mass of the planet. What's this? What's the unit of the mass of the planet? Yep, kilograms. I don't know what the hell that is. 5/97 times 10 to the 24. Okay. What about R? Kilometers. Let's keep it at meters for now, for simplicity. What about the mass of the object? Kilograms. So like this might get a little bit confusing, but we'll figure it out later. Megapounds.
Megapounds.
And then here's the tricky one. What's G? What are the units of big G? G must be nr squared over m squared.
Newton, what's R?
Oh, he's going off of the gravitational Newton's law of gravitation formula probably. But yeah, it should be so we have like G m over r squared is equal to a force, which is so if we replace these with unit stuff, right, then we get kilograms squared over meters squared equals to kilograms meter over second squared, right? So this becomes to the third. So G is equal to kilograms times meter third. Oh, wait. Yeah. Okay, so it should be meter cubed over kilograms times second squared. I think that's right.
Yes. Should be that. Mhm.
Kilograms squared. No, there's kilograms squared over here and kilogram over here. So it cancels out and it becomes 1/kilogram. Yeah, okay. So now we have that figured out, right? So, okay, so take a moment and figure out, oh yeah, also velocity. So the escape velocity is equal to what? What are the units here? Meters per second. Nice. All right, so like play around with the units here, and then you can either use the system of equations method with the powers, or you can, try to play around with it and figure out, like what is the combination of units that's necessary from like your masses, your radius, and your big G in order to get meters per second. This week's class feels like eternity. Why? It is fun.
Just like as a fair warning, we've kind of finished with like the physics. We're now going over annoying contest stuff. Like you won't see when you're studying physics in college, oh guys, let's do some dimensional analysis today. Like this is more for contest stuff.
The heck?
What's E?
Oh, escape velocity, VE.
Mass of Earth. Oh, I see.
And then that's MP, which is the mass of some planet. So Ivan says G MP over R squared. Does that work? What's this? So meters cubed over kilogram seconds squared times kilogram over meters squared. This becomes meter over second, no, meter cubed over, no, it just becomes meter over second squared, right? Yeah, I think I see one that's a bit better. I don't think the last one worked. So Muhammad says the square roots of G and P over R. And this becomes meter cubed over kilogram second squared times kilogram over meter square root. So boom, 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 boom. And this does indeed become meter per second, right? Cool. So we actually figured out escape velocity just by using units. You have to get rid of, you have to have the radical to get rid of the square on the second in G. Yeah, that's right. So that's one way to think about it, because big G is the only unit that actually carries seconds in the denominator, right? Which means that this has to be in there in order for there to be an S, and there has to be a square root on the G at least, right? So that's a good way to think about it. So yeah, so now we have VE is proportional to the square root of GMP over R. And like this is already correct up to a constant factor. So then, instead of having to remember like this entire spiel, you can just do this pretty quickly and then remember that there's a 2 here. And that's all you need to do to find the escape velocity, using only units and no physics whatsoever. Any questions?
What's the constant?
Huh? The constant is square root 2. That
It
does.
says it's proportional, so
Oh yeah. So if we add in the 2, then it becomes equal. Does that use some time though during contest? Well, yeah, it does. But then, of course, if you see the physics solution right away, of course, go for it. But then, there's probably gonna be some questions where you don't see the physics solution right away, right? So then you can already just do most of the work and say, oh, the answer has to look something like this, right? And then you can try to figure out, you can try to reverse engineer this preliminary answer that you got. You can say, okay, so what does this have to do with? Okay, so this is probably something to do with like gravitation. And then, you can figure out using like Newton's law of gravitation or potential energy or whatever the rest of the problem has to do with, right? Does that make sense? All right, I suppose we can do one more of these problems. Let me find one. Okay. I can't exactly explain this thing because I don't know it too well myself, but then it's something called a vibrating star. Okay. Don't ask me what this is. I don't know.
Wait, do you want to describe like what it is conceptually?
I don't know. You
Maybe.
want?
Well, okay, because vibrating star could mean very many things. Do you mean like a pulsar, like a neutron star?
It vibrates with a frequency.
I think that's a pulse variable. Let's see, vibrating star. Yeah, nope. All I get for vibrating star is
It's just a problem that I found.
oh, oh no, hold on. Vibrating stars could reveal elusive ripples in space. What in God's name? Okay, anyway, keep going.
Okay, chat's going wild. This is great. What's a vibrating star, guys? Yeah, okay. Don't all things that vibrate have frequencies? Yeah. So this star, as you might have guessed, uh, it vibrates with the frequency of nu. Okay.
The Greek letter, not the word.
And nu is written kind of like a V, but I'm trying to distinguish what the difference is. It's like this thing and curvy, right?
Like the symbol for a neutrino, yeah.
Okay, that's the best it's getting. So a vibrating star vibrates on a frequency V, nu, right? And then given a radius of r, mass density rho, and g, find proportionality in terms of r, rho, and g. All right. So I'm gonna let you do this on your own, and then you can DM an answer to either me or Andrew. Yeah. Oh, I got one answer. It looks good. Yep, that looks good. That looks a little bit weird. I don't think that works out. Okay, anyone want to go over it from the people who solved it? All right, I'm gonna just follow Ivan's instructions. Yeah, Lewis, that's right. So, so what are the units of each? I'll just do it actually. R is meters, density. What's density? Is kilogram over volume, which is kilogram over meter cubed, right? And then G, I have to go back. Meter cubed over kilogram second squared. Yep. Okay, so then if you play around with it a little bit, I guess, you have square root of rho G is equal to square root of kilogram over meter cubed times meter cubed over kilogram second squared. This is the square root of 1 over second squared, and this is just 1 over seconds, which is equal to the unit of frequency. All right, nice. So at the end of the day, I'm gonna just say like the purpose of unit analysis. It's 1, to check work. And then 2, partial solution in short amount of time. I'm saying like relatively short amount of time because it's probably faster than whatever physics solution you might have to come up with. All right. All right, so now with the remaining bit of time, I just want to go over the F equals MA that I posted. So I sent you like I sent you one from like a bit earlier because I thought, starting you off on one of the later ones was probably not a good idea. So then, but then we're gonna probably be skipping around. We're not gonna go in order because we're starting earlier. But yeah, the earlier ones are a tad bit easier. So do you want me to go over the buoyancy problem, or do you want me to go over the other problem, or any of the other problems? Are they graded, the forms? Yeah, I believe they are.
You're not getting into college if you scored anything below a 23.
All right, no, seriously though. Um, yeah, I mean, they're just to assess yourself.
No, I think they were returned. Did you return like the form so that they could see what they got wrong, right?
I think they see just directly after they do it, no? Do I have to do on F equals MA?
No, Arib, it's fine. You're good.
It helps.
It does. But you got 3 years. You're good. You're a freshman. Anyway, well, if they're not returned, then we'll have them. We'll like release the scores so that you can see what you did right, what you did wrong. Yeah.
Wait, actually, I'm gonna take a look at it. Give me 1 second. Wait,
While that's happening, oh, go ahead.
Oh, I got 2 submissions. That's sad. Please do the F equals MAs.
Like they're obviously like optional, as is basically everything is, because this is a club, not a class. But like it's very helpful, and it's just 75 minutes of your time.
First freshman to make USAFA question mark?
Maybe. Well, at least from Sty.
Wait, how do I check the thing?
In any case, while Alvin is checking that, and failing miserably at using Google Classroom, I'm kidding. For the F equals MA, I'm sure everybody here who registered, did you guys all register for the F equals MA? Like, please put like a thumbs up, check mark, whatever. Yes. Okay. Jeremy did not. Anyway, you might have. Okay. Well, I would double check that ASAP if you're not sure. I think like registrations are still going to be open. I think. Alvin, have they closed yet? Or
I'm not sure. I would ask Thomas.
if you got the confirmation email with the, oh man, Lewis, you're spoiling the surprise. Yes, you did it correctly. I was actually gonna like go right back to that prep book. So yes, everybody who registered for the F equals MA should have gotten a confirmation email from Mr. Thomas, who is our faculty advisor and the AP of the physics department and chemistry department. So he sent out just like general information and yeah. And attached to his email was a prep book, which contains like a bunch of past F equals MAs from like 2011 to 2019. And so it contains the practice exams, it contains the answer sheets, and it contains the solutions. So if you're, once you finish with your practice exam, like obviously check it over to see what you got right, but like more importantly, what you got wrong, look over the solutions, because the solutions will tell you how to approach different things. And if you just keep practicing and you just keep looking at those solutions, you'll understand like that a lot of those problems have like like similar solution methods. Like if you see like 4 different moment of inertia questions over the years, they'll all have very similar methods of solution. So yeah, just practice that. Like if you don't submit them for our classroom form, fine, like as long as you do them on your own time. Like we ask that you submit through the form just so that like we know that you did it. But do them on your own time and look through those solutions, just to understand what you did wrong and how to fix it.
All right.
Did you get it to work, Alvin?
Yeah. So
All right.
I see like among the 2 responses, Uh, yeah, please respond to the forum, guys. We want to have stuff to go over. We want to see like where everyone is. But so there were some people left a bunch of questions blank, and there's no penalty for guessing. So like if you just sort of guess all the questions that you didn't have the chance to do at the end, then you might have a chance to get some more points. In 2013 there was though, but we're practicing for the 2021 test, which doesn't, right? So
Oh, what is
I mean,
2013
I guess
there was?
there's no point in doing so for practice tests. Um, but yeah, during the real test, like if you don't know a question at the end after you've thought about it and you really just can't do it, then yeah, just guess and you will get some points probably. So it appears that the buoyancy question, which is question number 15, yeah, no one got that. And no one put a response either. Okay. Well, let's go over the buoyancy question. I know we're at the end of our time, but then just like stay for like 5 more minutes if y'all want to hear this. Okay, so the problem setup gives like this sort of rod thing, right? And this rod is suspended in a tub of water such that some portion of the rod is hanging outside of the water and some part is floating in the water, right? And it gives that the density of the rod is equal to 5/9 times the density of the water. So at equilibrium, so what portion of the rod is above water?
Oh, just before you even proceed with this question, no, that was my sibling, Mohammed. Anyway, before you proceed with solving this question, please don't try to look at the diagram and like try to calculate the area submerged with respect to the area not submerged. That's not gonna work. Please don't. Typically, these things aren't to scale. Like I did this once on the Amy and I got it right, but this isn't gonna work for physics. So like, don't try it.
Wait, did you actually?
I did. I graphed out a geometry question on the Amy 2 years ago, and like I just guessed some of the lattice points for the octagon, and I got it right. But don't do that here, please. This isn't math. Like they're not gonna try as hard to make it to scale. So please actually try to solve the problem.
All right. So here's what we can do. So we can let M be the mass, right? We can let the entire length be L, and we can let the part that is above the water be small l, okay? And the way we're gonna do this is because this is in a static context, right? Which means that the rod is in equilibrium, it's not moving. Then that means this is essentially just a statics problem where, you have sum of F is equal to 0 and sum of torques is equal to 0, right? However, because of like this hinge, which is attached to the ceiling, we can actually disregard sum of F is equal to 0 because like we don't actually know what translational forces are, what translational forces the hinge acts, the hinge has on the rod, right? So then, we're just assuming that it's whatever is necessary in order to keep the rod like not falling or moving from side to side, right? So then we can actually disregard this because of the hinge on the ceiling. And then we're gonna focus on the torques, right? Because the torque, in order for the rod to be in equilibrium, the torque about the hinge has to be equal to 0. All right. So firstly, we have to just list out what forces there are in total, right? So disregarding what is happening at the hinge, what forces are acting on the rod? Buoyancy and gravity. Good. Okay. So where is the gravity acting? On the center of mass. Physicists do research on more complicated stuff. It's kind of different, but the center of mass. What is mass?
I think he means mass.
All right, yeah. So gravity acts over here. What about buoyancy? Where does buoyancy act?
This typically is what trips people up.
All the points at the surface. Not exactly.
So let's try a simpler setup. What if this plank were flat on the surface of the water?
Yeah.
Where would the buoyancy act? If it were flat horizontally?
At the center of mass, right? So then now, if I were to take like a part of the rod and stick it out of the water, right? Where would it be now? Through the point 1/2 from the top of portion underwater. Yeah, because the buoyancy forces doesn't care about the part that's out of the water, right? It only cares about the part that's in the water. But like once it like looks at the part that's in the water, like it acts on this entire portion of the stick uniformly, right? So that's why we can say that the buoyancy force acts on the center of mass of this part in the middle, right? So then, yeah, any questions? Yeah, and it's also due to the fact that it's uniform. But it actually doesn't matter that it's uniform because I can have like uh, some large thing here and then some small thing here. And they're like of like unequal densities, but it'll still act like here. I don't know. Questions? All right, no questions. Then yeah, so the force of buoyancy is going to act actually over here. Or like somewhere over here, just in the drawing. This is the force of buoyancy, and that's the force of gravity. Okay. So now let's calculate torques about the hinge. There's enough space. I don't know. Torques. So torque due to gravity is equal to big M times G times times L/2. But then we have to consider the angle, right? So then let's consider the angle from the vertical. So if that's theta, right, then this angle is like, what is this angle? It's 90 plus 90 minus theta, right? Yeah. So then sine of 180 minus theta, that just becomes sine of negative theta, but then, so then we just take that as, we just take the magnitude, right? We take that as the torque pointing like in this direction. Yeah, so mg L/2 sine theta, right? But then what about the torque from the buoyancy force? The torque of the buoyancy force is equal to, okay, so let's think about this, right? So the force from the buoyancy force is going to be equal to the weight of the water that's displaced by the thing, right? So then let's just call this W for now. But then this angle is again going to be theta, right? So then we have again is like sine theta. So then we have like the weight of the water that's displaced times g times, all right, and then what is the position of this, the center of mass here in expressed using big L and small l? I'll just say it's going to be L plus L over 2, right? Because it's the average of the entire stick and the part of the stick that's out of the water, right? And that's going to be like the midpoint. So big L plus small l over 2. And then we're going to again add sine of theta, right? Yeah, okay. So then we have to set these equal to each other in order for it to work out. So W times sine theta times L plus L over 2 times G is equal to, I don't actually have to add G because I included G in the weights, right? And this is equal to, oh yeah, if you have to go, you can go, by the way. We're going a bit over time to discuss this buoyancy problem. Yeah, so this is equal to mg L over 2 times the sine of theta, right? And then these can cancel out. And also, okay, but then what is like W? So W is the part of the stick that's in the water, right? So first of all, the volume is going to be, or the mass of the part of the stick that's under the water is equal to m times like 1 minus L over L, right? So this is the mass. But then we also have to account for the density differences because we want to have the weight of the water instead of the stick, right? That's the magnitude of the buoyancy force. So we have to multiply this by the density of water over the density of this rod, right? And then again, of course, we have to multiply by G. So what we're left with here is m times 1 minus L over L, rho water over rho rod times G times L plus L over 2 is equal to mg L over 2, right? Okay, what can we get rid of here? We can get rid of mg, right? Yeah, and then rho W over rho rod. So rho W over rho rod is equal to 9 over 5. All right, GTG. All right, goodbye. So this becomes 9/5, right? So 1 minus L over L times 9/5 times L plus L over 2 is equal to L over 2. Right, okay. So now we can actually divide by L over 2. We're multiplying by 2 over L, right? So then we have 2 over L minus 2L times 9/5 times L plus L over 2 is equal to 1. And then we can actually put this on that side. So that's equal to like 5/9, right? Multiply by 2, we get 10/9, and we can get rid of this. Now it just becomes like solving. So we can also divide by 2 here, and then we get back 5. So 1 over L minus L times L plus L is equal to 5/9. Is this right?
It looks right. Are you? Yeah.
This unit combination doesn't make sense.
Yeah. This doesn't seem like a 3-minute
This
problem.
doesn't. All right, we'll continue this next time. We're during office hours. At the end of at the end of every meet, my brain just becomes gloop.
Okay, so like
I did something wrong, but yeah, you guys like understand how to solve this. So then for next time, try to clean up my solution. All right, I'll be posting these slides.
just one note, like on math, on like the way the ethicals MA is structured, it's not like the AMC 10 and the AMC 12. Like, what do I mean by that? I mean, like the first 5 questions on the AMC 10 and AMC 12 typically are solved within like 15 seconds. Like they're very easy. And then, they get progressively more and more complicated as you go through to the point that like the last 5 questions actually take time. You don't, that's not, no. F equals MA is not that, because that's not how physics works. It's not like you get progressively more complicated. It's the topics are all different. So sometimes question 3 will be this and take like 15 minutes to solve. And question 22 will take like 30 seconds because it's a question on, how to set up an experiment, right? So be careful with that. And like recognize that like, unfortunately not all things are 3-minute solutions, but it will compensate, like, because there are other like problems that will be like 30-second solutions because, how do you set up this experiment, this and that. So just, should we do the 30-second one first? What you should do is you should read through all the problems first.
Yeah, and
Like,
try to know which ones you think you have to skip, because yeah, the problems aren't rated based on, they don't go in order of difficulty. So
they don't even go in order of topic.
yeah.
So if like what you could do, what I tried to do when I was practicing was I would try to separate them by topic. Like give each topic like a certain symbol. Like I don't know, like a triangle is your Newton problems, and like a star is gravity. And then go based on the order of difficulty for you of the topic. If like gravity is easy for you, do the gravity ones first. Like I would do that. Obviously, with 75 minutes, that's not a lot of time, but thankfully, because it's going to be over AOPS, bubbling is not an issue. You're going to just be typing A, B, C, D, or E into like a text thing. So you won't have to like worry about bubbling. Like as soon as you solve a problem, you'll just jump to the question on AOPS. But the only way and the best way to understand like what strategy works is to practice. Like go through a few, understand like, how many problems on the ethicals MA will you typically encounter that take more than 3 minutes that you will have to save. Because if it's like around 10 questions, then, you really got to be very good at isolating those 15 other questions that will not take as much time. So just practice a lot. Sorry, Alvin, if I interrupted you, my bad.
No, it's fine. Yeah, so that'll be all from me today. For next week, I'll put up another test. Also, like try to submit a file that's like that cleans up this solution. That'll be the other one problem. Was there a problem from earlier as well that I
I think
wanted
there was.
to?
No?
No.
No problem? Or is Jeremy just saying that because he doesn't want more homework?
No, he
That's
went
like-
over it.
yeah, I don't think I had anything else. Yeah, so just like try to clean up my solution now that you know the method of doing so. Yeah, that's all. Hope you all have a great week. We'll see you next week.
Or on Saturday.
Yeah, oh yeah, office hours are still a thing. For anyone that's still interested. Goodbye.
Bye.
It always stays behind. Do you have a question for us, Charles?
No.
Okay.